Hello everyone, welcome back to my YouTube channel. Today we are going to study diffraction. So, what is diffraction? Diffraction can be thought of as a special case of constructive and destructive interference. Okay. Okay. A case where there are a large number of scatterers. So, diffraction it sometimes seems as a mysterious phenomena which is difficult to understand. So, electromagnetic waves, it is EM waves like light, X-rays, UV rays, gamma rays, etc. Water waves, that is elastic waves in fluids or solids. Then matter waves, that is electron or neutrons. Etc. These all can be diffracted. It is not like only the EM waves can be diffracted, but all the others can also be diffracted. Now, we know what all can be diffracted and what is diffraction. So now, diffraction is caused majorly by these scatterers. Now, what are these scatterers? To answer this, we say any entity that will restrict the motion or restrict the path of the wave. By restriction, we can say it redirects or gives a new direction. Okay, they can be termed as scatterers. Okay, so one entity can be considered as a scatterer for one kind of wave but not for the other. For example, an array of atoms that is a scatterer for X-rays, but it cannot act as a scatterer for water waves. Okay. Now, experiments have been conducted where matter waves have been diffracted from a crystal made of electromagnetic radiations, that is, atoms diffracted from a laser lattice. Okay. So, what is the bare minimum need, what is the bare minimum thing that we need to see diffraction or interference? What is the minimum need to witness diffraction? Okay, so bare minimum we need is 1 edge or 2 edges forming a single slit is always better. So bare minimum is 1 edge. So if this is your scatterer, your wave can scatter from this edge always. Next is we can have 2 edges that will give us a better picture. 2 edges they form single slit, okay, or double split, double slit, sorry. We very well know about the Young's double slit experiment. Okay. Now, in very common languages, diffraction can be stated as bending of waves around the edges. Okay. Now, when a wave encounters a slit, this leads to intensity in the geometrical shadow regions. Okay. So, whenever you have a slit, so there will be edges. So, this can bend the wave. Now, as a result, intensity can be found in regions that are not in the line of sight of the wave, of the incident wave, rather, I should say. Okay. One of the methods to understand this is Huygens wavelet construction. This is one of the ways to understand the formation of intensity in the geometrically shadowed regions. Okay, so here each point in the unobstructed wavefront is considered as a source of wavelet, and these wavelets, they propagate to the screen and form interference patterns. Now, we see why. Now let us see some examples. Suppose we have this slit. Now certain waves are coming, separated by some distances, and these actually do not hit the edges. So the waves in the middle, they pass as it is and form a continuous intensity on the screen. Suppose this is your screen. So what they will be forming, the intensity will be like this. So this is 0, and corresponding to this will be 1. Okay. So this will be the intensity on the screen. This is 0 and this is 1. Okay. So it is to be noted that these do not hit the edges. Hence, they pass straight through the gap. And these ones, they are obstructed by the obstacle, and they reflect back. These waves, they reflect back. Okay. Now, what happens when these waves hit the edges? Okay, let us see. Suppose we again have some slits. We have these slits. Now we have incoming waves. So these are the incoming waves. Now one of the wave hits the edge. These other pass straight. Now one hits the edge. These ones that are obstructed till this one and these one, they are reflected back because of the obstruction. They cannot pass through. And these three, these three, they continue straight to the screen without any kind of bending or anything. But here, this one and this one, these bend because they hit the edge. So after bending, suppose we have a screen at a far off place. Suppose this is the screen. Now after bending, this goes something like this and this goes something like this. Okay, so in the intensities, what we have is the rest of the things have intensity of 1. Okay, and here we have a higher intensity. So where, sorry, so here we have 0 because no wave is coming through. Now we start to get intensity 1. Now we, because here we have extra waves, so it amplifies and it goes like this. This is the highest and then it drops. Then this, okay, sorry. So let us draw it like this is the highest and it drops this, and then this is the highest and then it like this. So this is 0, this is 1, and these two humps, they are actually greater than 1. Alright, so here we get extra intensities. Okay, so this is actually not a peak but a broad diffused peak, we can say. Now, what if the slit is of the width of the wavelength of this wave? Now, what happens if the slit is of the wavelength of the waves? As discussed in the previous lecture, in such a case, diffraction will occur. So, for when there is diffraction, we will get an intense peak. Okay. So now let us have a smaller slit. Suppose this is the slit of the order of wavelength of the waves, and these are the waves that are incident on the slit. Very closely spaced. Okay, and now Here further we have the screen. So here now the grid spacing is of the order of wavelength of the wave. So this spacing of the grid is almost equal to the wavelength. So now we'll have intensities such that we'll get a peak. This is 0. Okay. So these are the peaks, and we can clearly see that we get some intensities in the shadow region as well. Why this is called the shadow region? Because this is the region which is actually obstructed by this obstacle. Okay, so this is not in direct line of sight of the incoming waves. Okay, so we see to get proper intensities, we need to satisfy the condition that lambda is approximately equal to A. Okay. Now, once we have understood how we get intensities, let us go on to constructive and destructive interference, that is diffraction. Okay. Okay. So, first go with the constructive interference. So, what do you mean by constructive interference? As the name suggests, this is the addition of intensities basically. So, we get amplification or higher intensities. Okay, so here we see how waves are scattered from two successive planes. Okay, so suppose we have two planes. This is plane 1 and this is plane 2. This is plane 1 and this is plane 2, and incoming waves are scattered from these planes. So suppose this is the middle section. So this is X, this is Y. Okay, so and these are the center lines of the incoming waves. Okay, and these are the transmitted waves. So this is incident and this is diffracted or scattered. Okay, now let us draw the different wavelengths. So one is the incident wave goes like one wavelength and two wavelength. Sorry, suppose it has one wavelength, two wavelength and half wavelength. Similarly, 1, 2 and half. Let me draw more properly. So this is one wavelength, two wavelength and half. Okay, and now on the other end, this is we get similarly we get 1, 2 and half, and from here similarly I get, so suppose these are the perpendiculars, so what I get is this again 1, 2 and half. So what about this extra wavelength? So this extra wavelength here and this extra wavelength here, this is half. So they constitute one complete wavelength. So this is suppose A, this is B. And suppose the spacing is D, H, K, L. Now the phase difference is pi, 180 degrees, okay, upon scattering by atom Y. Okay. Now the extra path travelled by wave 2 is lambda by 2 plus lambda by 2 is equals to lambda, that is one complete wavelength. Now for constructive interference, the phase difference should be an integer multiple of pi. Integer multiple of lambda. Okay. So it can be lambda, 2 lambda, 3 lambda, 4 lambda and so on. So here when the path difference is of lambda, so we say these waves interfere constructively. Okay. Okay. So this is constructive interference. So if the path difference is lambda, suppose this is your A, B, C and your path difference is just lambda, then this is called first order reflection. Now suppose if your path difference is 2 lambda, suppose one complete wavelength of this and one complete wavelength of this, then this is called second order reflection. And considering this, if the path difference is 3 lambda, then it is third order reflection. If it is 4 lambda, then it is fourth order reflection. Now moving on to the next one, that is destructive interference. So as the name suggests, destructive interference refers to the destruction of the intensities. So when two waves interfere destructively, the intensity of the peaks is reduced or intensity becomes almost zero. It can vanish as well. Okay. So now it is easy to visualize what is destructive interference. So suppose you have two planes, plane 1, plane 2. Interplanar spacing is B. Now suppose this is the central line, okay. Now suppose you have incident rays. This is the incident ray and you have reflected ray. These are the reflected one. And now we draw perpendiculars from here. Now if your phases are like this, supposedly this one goes like this, whereas this one goes like this. So this is negative and this is positive, so they completely cancel each other. So the resultant intensity would be 0. This is a case of exact destructive interference. Now, a situation can be such that this is not exact, but they are out of phase by some other angle. Now, suppose this is your plane 1, plane 2, interplanar spacing D, and we have these central lines. Okay, now we have incident rays and the reflected rays. Now suppose, now draw perpendiculars from the above plane. This will be the region of path difference. Now suppose the above wave is like this, okay, but the wave in this plane 2, it is not completely distracting it, but slightly. So there is a slight shift. Sorry, let me make it more. So it will be like, okay. So there is slight shift in the peaks. So this will not completely nullify the intensity, but will reduce it to some extent. So this is also destructive interference, but not complete one, a partial one. Okay, so this was about diffraction. Now, some aspects related to diffraction. Okay, so diffraction needs certain important conditions that need to be satisfied. So, what are those conditions? Diffraction requires three important conditions to be satisfied. So what are those? First one, that is radiation related. So here we say that all the waves should be coherent, monochromatic, and parallel in nature. Okay, of wavelength lambda. Alright. Now the second one is sample related. So for this, from the sample perspective, we should have a crystalline array of scatterers. We should have a crystalline array of scatterers. Alright, whose spacing is equivalent to the wavelength of lambda. Alright, now the last one is related to the diffraction geometry. So the last condition is related to diffraction geometry. So for that, Fraunhofer diffraction geometry should be satisfied. Fraunhofer diffraction geometry. Okay. Are the conditions that are important and they need to be satisfied for the diffraction to take place. Now, in such a scenario, we get, if these are satisfied, we get diffraction patterns with sharp peaks. All these results into diffraction patterns with sharp intensity peaks. Okay. Now, we have already seen that the waves can be electromagnetic, matter waves, sound waves, water waves, etc. Now, what is Fraunhofer diffraction geometry, which we have mentioned here? Fraunhofer diffraction geometry simply implies that parallel waves are impinging on the scatterers. And the screen is placed far away from the object. Okay, so this is Fraunhofer diffraction geometry. Now, after we have realized this diffraction phenomena, let us move to X-ray diffraction. Okay, that we'll continue with in the next lecture. Thank you.